Science Alliance. There's no excuse for the faffing today, is it? I can't pretend that I was writing a book. I very clearly just got out of the shower. Thank you for your patience. Hello, IGCSEers. Lesson 7. We're going to do something we never normally do. We're going to recap on last lesson. Do you remember we did series and parallel circuits? We looked at how a series circuit is a complete loop, and a parallel circuit is where the wires sort of branch off, so the split, the current has to choose which way to go. And our brains melted too much, and we have 2 worksheets left. So I thought it's always a good idea, actually, to kind of duck into previous subjects as you go along, so you don't forget it all. So first of all, can you just do this little recap quiz for me, please? Series or parallel? Come on, it's not very hard, this one. I'm not going to give you very long. You've got 6 circuits here. Are they series or parallel circuits? One of them is a complete loop with 4 bulbs. The other one is a cell, and then it sort of splits and does a figure of 8, and there's a bulb on each side. One, it is a complete loop, but it's very wibbly. 4, you've just got a complete loop, it's got an ammeter in it. 5, you've got a loop of wire with 2 bulbs in, and that's connected to another loop of wire which has another bulb in and a cell. And number 6, you've got a complete loop with a bulb, and then the wires split and they're attached to a voltmeter. What do you reckon? If you've already finished and you're bored, you can always like and subscribe. Let's go through the answers. Question: a series. The first one is a series circuit. Number 2, that is a parallel circuit. Look, the wires are splitting. Number 3, that wasn't very hard, was it? It's just a wibbly one, but it's still a series circuit. It's still a complete loop. Number 4 is a series circuit as well. It's a complete loop with someone measuring the current through the bulb. Number 5, kind of both. It's like a combined circuit. I've put parallel because obviously the wires do branch, don't they? There is a split there. You get to play with those a lot at IGCSE, at A-level physics. And number 6 was the one that I thought might catch you out. That is a parallel circuit. Sorry, it's a series circuit, but someone is measuring the voltage across the bulb. But it wouldn't make it, so the wires are branching, but because it's just a voltmeter, we say it's a series circuit. It wouldn't make any sense if when you tried to measure something on a series circuit, you turned it into a parallel circuit. All right, next one then. Decide if each sentence is talking about series or parallel circuits or both. So if one bulb breaks, none of them light up. Is that a series circuit or a parallel circuit? If a circuit has 2 switches, both of them have to be pressed to make the machine work. Is that series or parallel? Which one uses less wiring? Which ones, the bulbs share voltage, so the more bulbs you add, the less brightly they shine. Which one is it that the bulbs shine with the same brightness, however many are added? Weird. And if one bulb breaks, the other one keeps working. What's that about? What is that about? Okay then, very quickly. If one bulb breaks, none of them light up. Yeah, that's the 90s Christmas light scenario with a series circuit. The series circuit, if it has 2 switches, both of them have to be pressed to make it work. That's how lawnmowers work. Series circuit also uses less wiring. It's not very imaginatively laid out, this, is it? Bulbs share brightness in a series circuit. Well, they share voltage, so they shine less brightly. But a parallel circuit we learned last week, you can add as many bulbs as you like, and they'll all shine with the same brightness. So odd. And if one bulb breaks, then you've still got a complete loop, so the current can still flow. There you go. Right, moving on then. Because today we're looking at all the graphs, which is a really important one for your IGCSE. We're also doing a little bit of mopping up, and I'm telling you some really important things that we haven't talked about so far. So the first thing I want to talk about is this. Oh, I can write forwards. She always says each week, because it's on YouTube. V equals IR. Okay, it's not new to you, you've seen this before. Voltage equals current times resistance. We've been using this equation as if it's just like a handy way to work out problems, which it is. It's actually an incredibly deep and important relationship. It's one of the most important equations in physics, I would say. It helps if we rearrange it to current equals voltage divided by resistance, because then we can see the relationship better. Cast your mind back. I think it was the very first lesson. We were talking about speed and distance and time, and we were talking about relationships that were directly proportional. You remember that? So if resistance stays the same, say you've got a simple circuit, the resistance of the circuit is staying the same, you can see this is a directly proportional relationship. When the voltage doubles, the current doubles. When the voltage trebles, the current trebles. It kind of makes sense, right? If you push twice as hard, then you get twice as much current. So, you know, if you remember that lesson, you know what I'm going to say next. If you've got a directly proportional relationship, then you can build a circuit where the resistance stays the same, change the voltage, see what happens to the current. Write some numbers down, maybe get a little graph going on. Have a look at this. So this is a symbol for a fixed resistor. It is the most tedious circuit symbol you can get. It's just a rectangle with a line on either side, but not going through it. So say this is a mystery resistor. We don't know what resistance this resistor is. Exciting. You measure the voltage across it. You measure the current going through it. This isn't a very good diagram because we've got no way of changing the voltage. So usually this would be a power pack and you could crank it up to like 1 volt, 2 volt, 3 volts and see what happened to the current. And you would end up with a table of results. And with the table of results, you could draw a graph. So let's just do a little recap on graphs. Remember about 1,000 years ago when we did distance time graphs. If you've just joined for electricity, this was the very first lesson we did, but I will recap. So we were looking at how speed equals distance divided by time. So you can work out speed from a distance time graph like this. So say you've timed someone running and you know the distance that they travelled and what time it took them to get there. You put distance on what's called the y-axis, the one pointing up, and time on the x-axis. You know that speed equals distance divided by time. So to find the speed, we do something called working out the gradient, okay? So you would choose, you make it a nice big triangle if you can. Choose a big line going down to represent the distance. So we'll go from this point on the graph here. This line represents 8 meters, okay, on this graph, like from there to there, 8 meters. And that line coincides, when that point is at 8 meters, it's also, can you see, 4 seconds along the bottom. So you basically draw a triangle, yeah, taking a gradient. This isn't new. And then you can just plug it into the equation. So we've got 8 meters and 4 seconds. So 8 meters divided by 4 seconds is 2 meters per second. So don't worry if this is going quite fast because it's recap for most people. But basically, when you draw a graph, you can, if you've got an equation that matches the graph, you can work it out. So here is a graph that you would draw if you were working out the resistance of a mystery resistor, okay? You put current on the x-axis, current on the y-axis pointing upwards, and voltage on the x-axis. And here we've got our little Ohm's law equation, I and V and R, in a rectangle. I'm just going to pull you back up because I feel like you've been pointing away from me for a long time. So this equation is often referred to as like the Ohm's law equation. You remember Mr. Ohm gave his name to the unit of resistance, the Ohm. And it's Ohm's law that says that current and voltage are directly proportional, okay? So a fixed resistor obeys Ohm's law. So if current and voltage are directly proportional, then we're expecting a straight line graph, right, from this activity that we're doing. So let's have a look how you can find out the resistance of the mystery resistor from this graph. I'll show you. This is where a lot of people are describing this lesson on Facebook as brain melting. So yeah, sorry about that. But anyway, if you measure the potential difference somewhere along here, and you get the current, which is somewhere along here, and you divide the potential difference by the current, you get the resistance. Yeah, look, because voltage divided by current equals resistance. Let's have a little go. Here's an example for you. I've written resistance equals voltage divided by current at the top. We've got a straight line graph that someone's drawn from their results. So I'll measure a current here, which is 8 amps, keeping things simple. And we'll measure a voltage along the bottom that kind of matches that 8 amps, which is 4 volts. So you just plug it into the equation, yeah? Now you've got to be a little bit careful. We're not actually working out the gradient, are we? Because the gradient is the long one over the one that's across. The gradient would be 8 divided by 4. But look, we've got voltage along the bottom. So we've got to do voltage divided by current in this case, which is 4 divided by 8. So the resistance of this mystery resistor is 0.5 ohms. Now, stick with me. This might melt your brain a little bit. The gradient of this graph, if we'd done 8 divided by 4, that would actually give us 1 divided by the resistance. So you could do it another way. You could do 8 divided by 4 to get the gradient of the graph like we were doing with our distance time graphs, and that would give you the number 2. But you just have to remember, okay, the gradient of the graph is 1 divided by the resistance. So 1 divided by resistance equals 2 in this case. And then you can say, oh, okay, so the resistance is just, we rearrange that and we get 1 divided by 2, which is still 0.5 ohms. Some people find that a bit brain melting. I find it easier to just go, okay, resistance is voltage over current, so I'll get a value for voltage and I'll get a value for current and I'll stick them in. But it is entirely up to you. Okay, have a go yourself then. Can you find the resistances of these fixed resistors? I've been lazy, I haven't put numbers on. I'm just going to say 1 square equals like 1 amp or 1 volt. So you've got mystery resistor A and mystery resistor B. So someone has put a fixed resistor into a very simple circuit, measured the voltage and the current as the voltage changes, and plotted some points on a graph. What's the resistance of A and B? This is super mean, isn't it? Because I haven't even put the equation on. You've just got to remember that V equals IR. But I don't think you can do it. And if you can't do it, it doesn't matter, because I'm going to give you the answer in a sec. You don't need to have understood everything straight away. How are you getting on? What do you think, 10 more seconds? I'll draw something on the board. Right, then let's have a go. So, number 1, well, you can just choose any point. It's not wrong. Generally, you make the triangle as big as possible. I've started 1, 2, 3, 4, 5, 6 squares up, so I've got a current of 6 amps, yeah? And the corresponding current, this corresponding potential difference or voltage is 6 volts, yeah? So I've got a voltage of 6, a current of 6, and resistance equals voltage divided by current. So 6 volts divided by 6 amps, so it's 1 ohm. Well done if you got that. And the second one, I've got a current, I'll just go right to the end. So I've got a current of 2 amps there, and I've got a potential difference along the bottom of 6 volts. So resistance is 6 volts divided by 2 amps, which is 3 ohms. Well done if you got that, and if you didn't, it doesn't matter. Let's talk about something else. This is the bit that I think might make you angry. With physics, I got very angry with my physics teacher about this. She probably got very angry with her physics teachers about this. It's a great cycle. Now, we've talked a lot about how, it's worth saying, by the way, this is a cell here, isn't it? It's a symbol for a cell, a long line and a short line. We have mentioned it, I'll mention it again. The short line represents the negative terminal of the cell, and the long line represents the positive terminal. So we've talked a lot about how there are electrons, tiny little sort of particles in the wire that are negatively charged. And negatively charged things are repelled by negatively charged things and attracted to positive things. So we've talked a lot about how electrons in the wire move away from the negative terminal of the cell and towards the positive side, which is true. That is what happens. Unfortunately, when humans first started playing with and discovering electricity, we didn't know about electrons. We had no idea what was happening in the wire, and we just started saying that electricity flowed from the positive terminal to the negative terminal. Obviously, that is not right, because that's not what electrons do. They don't move away from positive things, but it is what's the convention. Because by the time they discovered electrons, they were like, it's too late now, we've already kind of designed everything. So this made me furious. It's like, why can't we just change it? But no, we can't, it's too late. What does it actually mean in reality? Your exam question will always make it very clear, like what it's asking you, so don't panic about which one do you use. But it just means that how like the symbols are written on equipment and how equipment is designed, it's designed as if current flows from positive to negative. So the time that you might come across it is if you're sort of playing with like ammeters and voltmeters and bits of equipment, you might sometimes see the voltage or the current has a negative sign in front of it. That means that the current is travelling in the opposite direction to what the equipment thinks it should. I'll show you. That's the easiest way. I've got my adorable little circuit here that I'll show you. Here we go. So I've got a bulb, just screw it in so it works. Got a battery pack, 2 wires connected to a bulb. Have a look on the battery pack. You see a little plus sign, yeah? So convention has it, it's not true. What convention's saying is happening is that current is flowing from this positive terminal through the wire and through the bulb and then back to the negative terminal, okay? That's what convention said. I've got my little voltmeter here, bless it. It's a bit well used, but it's hanging in there. So I'll attach this in parallel across the bulb, yeah, to work out how much energy per charge is going through this bulb. Now, this voltmeter is designed to think that the current flows in this direction as well. So if I read my voltmeter, oh, look at that, lovely. Exactly 3 volts, yeah? Isn't that great? Because I've got a 1.5 volt cell in parallel here. So that's what we'd expect. If I cross these wires on my voltmeter over, put one on that side and one on that side, what are we going to see on the voltmeter? What do you reckon? Well, what would convention have it is happening? Current is now flowing from the positive terminal, but through the wire into the other side of the voltmeter and then back again. So the voltmeter, bless it, if I give it a little tap here, can you see, look, it's reading a negative value. Now, this is a very small and sort of a toy voltmeter. A real voltmeter will usually have negative numbers as well. So if you saw like well, I'll flip you back a bit. So usually, like if you're doing this fixed resistor experiment and you see a -2, you could just ignore it and just write 2. Makes no difference because you're just measuring energy per charge. It doesn't really matter which direction the current is flowing in or the voltage is. But this is why that happens, okay? Because the current is flowing through the voltmeter kind of in the wrong direction, yeah? Because I've crossed the wires, it's now going from left to right instead of from right to left, so we've got a negative. Okay, so that's what that means, and that's why when you look up the proper graph on your BBC Bite Size or whatever of what a fixed resistor looks like, it looks like this, because we've got a negative side and a positive side, yeah? So that's the current 1, 2, 3, 4, 5, and this is the current -1, -2, -3. And this is the negative potential voltage, -1, -2, -3. But as you can see, it's exactly the same relationship on either side. Okay, let's have a think about components, stuff that you put in circuits that do not obey Ohm's law. Some of them don't. For that, we need to clear up another, I think, misconception. That means like thing that we're all thinking wrong. It's thing that we're all thinking, but it's wrong. Here's what's happening inside a wire. Again, we've talked about this a lot, and I keep saying that inside a wire, there are positive particles which are sort of fixed in position. They're not totally fixed. Everything in the whole universe is vibrating a little bit. So all these positive particles are kind of vibrating, but they're in a kind of fixed position. They're vibrating around a fixed point. Now, I think I might have given you the impression that these positive particles are protons, and they're not. No, they're not. You know what an atom is? If you've been to my if you came to my all ages home ed lessons on the periodic table, it's very useful for this bit actually. So an atom, very quickly, because I'm sure you know this, is positive particles called protons with teeny tiny little particles called electrons kind of whizzing around the outside. And we learned in that periodic table lessons that I did that the electrons are actually arranged in shells, kind of like that, right? So different layers of electron shells. What these positive particles are, they're not protons because they are actually just atoms, but that have lost a few electrons. So in the periodic table lesson, we were looking at how metals in particular lose their electrons quite easily. So they're still atoms, but they're a little bit positive because they've lost some negativity. Is that all right? Electrons are negative, so if you take some electrons away from an atom, you've got a more positive atom. The proper word, if you're following this, if you know about this already, the proper word is ion. An ion is just a positively charged or negatively charged atom. So these are positive ions in the metal. But if you don't like that and you want to call them atoms, I think that's probably fine as well. If you get to A level, you'll definitely have to call them ions. So I could have drawn like this, little electrons still around some of the ions, but I just wouldn't because it looks silly and it would take too much time. But yeah, that's what's happening. So the electrons, everything else that I've told you is true. The little electrons, some of them are free in the wire, and it's the free electrons that flow, and that's what the current is. And obviously the electrons do collide with these positive particles, the ions, and that's what resistance is, yeah? The harder it is for the current to flow, that we say the more resistance there is in the wire. So longer wire means the electrons are colliding with these positive particles more. And yeah, it wouldn't be an electron colliding with a proton. That wouldn't make any sense. If that happened, that like magic would happen. It's just an electron colliding with a positive particle and then bouncing away. So let's dig in a little bit more to resistance. We've done this before. If you rub your hands together, what you're actually doing is you're knocking atoms in your skin into each other. And when things knock into each other, they move around more. And when things move around more, it's basically what heat is. So this, we've looked at before, this is why wires get hot, because of all these collisions going on. So these positive particles start to vibrate more. They vibrate more energy, and that's what heat is. It's particles moving more. Okay, whew, so much talking. I'm going to give you a description that someone's written about resistance in a wire, and I want you to correct it. And then I've got a little task for you. I think we're done here. Here you go. Basically, what did I just say, children? What is wrong with this description? Someone has written, resistance is caused by free electrons colliding with protons in a wire. The protons start to vibrate, causing the wire to warm up. So what's wrong with that? You're IGCSE students, so I'm not going to tell you how many corrections you need to make. Just correct that, please. And when you finish correcting it, pedants, it's not about punctuation, okay? A lot of people complaining on Facebook that I hadn't put a full stop at the end of the sentence. That's not what we're talking about here. When you've done, can you have a look around your house? I've put brackets kitchen, and find something that uses the fact that wires get hot. You definitely can. Your kitchen isn't even a kitchen if you don't have something that makes the wires get hot, that uses the fact that wires get hot. Should we go through it? Okay, resistance is caused by free electrons. Yep, that is true. There are free electrons in a wire. And they colliding. Yeah, that's true. That is what resistance is. Harder for current to flow. With protons, gasp, no. You can write ions or atoms for that. The protons start to vibrate. No, they do not start to vibrate. We'll do a lot more of this when we do the energy topic. They don't start to vibrate, they just vibrate more. But that does cause the wire to warm up, yes. And did you find something in your house / kitchen that uses the fact that wires can get hot? This is on your IGCSE specification that you need to know this. The main one is toasters. So basically anything with a filament in it. A filament is like a very tightly coiled piece of wire that is deliberately designed to make it as hard as possible for the electrons to flow through it, so that you get loads of collisions, generate loads of heat. So a hairdryer uses a filament to heat up the air, or kettle, it's got a filament in it, anything like that. Light bulbs, back in my day, used to be filament bulbs. They had a filament inside which was designed to make it so hard for the current to flow that it got so hot that it gave off light, which was a genius idea, but also incredibly inefficient. What a waste of energy, again, which we will talk about later. But still, one of the classic graphs that you have to know about for your IGCSE is the graph that you get if you measure the current and the voltage going through a filament bulb. So let's have a little look at that. Here we go. So this is the setup. Again, it's not, we'll talk about this later, you'd need a power pack so that you could change the voltage through the bulb and measure the current. And eventually you would get a table of results and you'd plot them into a graph. Have a go. So I've put resistance is increasing. when you turn on a filament bulb, it gets hotter and hotter and hotter. There's more and more and more collisions generating more and more and more heat. So what does a graph look like where the resistance is increasing? If you remember, like acceleration, distance, time, I'm going to give you a second and then I'll do it. Some of you, if you've been to my Facebook group and you've got the sheet, you've got the answer in front of you. So I've said, if you've got the answer in front of you, can you sketch one with voltage on the x-axis, on the y-axis, and current on the x-axis? Put voltage on the top and current on the sides. I find that a really difficult task. I'm going to do it in front of you because I think it'll be interesting for you to see me suffer. And you know, I think it's good modelling for what I would have to do in my IGCSE. But come on, get some brain exercise done. What do you think? I think it's good practice for us all to struggle. 5 seconds. Go on, sketch it. Resistance is increasing. What's it going to look like? 5, 4, 3, 2, 1. Okay, what you will see is something that looks a bit like this. Kind of a nice big sweepy S shape. Right, I'm going to have a go. Here we go. Come watch me suffer. So that's the classic one, because we do usually put current on the top. But that's unlikely to be what they test you on, right? Because anyone can just remember the shape of a graph. You have to show that you have understood the graph. So here we go. I'm gonna try and do it too. I'm going to put some little divisions on for current and voltage. So what does a filament bulb look like if the voltage is on the y-axis? Well, resistance increases. So first of all, you apply a little push, right? First of all, if there's no voltage, if there's nothing pushing the electrons around the circuit, then there's no current. So I'll put a 0 there. First of all, I guess you would say it kind of obeys Ohm's law. When you get an increase in voltage, you get an increase in current, increase in voltage, increase in current, and then you increase the voltage, but you don't get as much current flowing. Like you're trying to push, but there's just not as much current flowing because the resistance is increasing. Oh, there we go. Yeah, it's not too hard, is it? Yeah, so lots of voltage, not very much current because resistance is increasing, so I've got a graph that looks like that going up to the sky. Well done if you've had a go at that. Very well done. I find this really tricky. And then it would be the same on the other side. Doesn't matter if there's a negative sign there. Right. So clearly we can see a filament bulb does not obey Ohm's law. Voltage and current are not proportional to each other. Remember back in the day we learned that if something's directly proportional, you get a straight line. It's not a straight line. Let's learn about something else fun that doesn't obey Ohm's law. First of all, Ohm's law in words. Here we go. That's why you will see something like this if you look up Ohm's law on BBC Bite Size. Voltage is directly proportional to current as long as temperature stays the same, is essentially what that is saying. As long as all physical conditions, such as temperature, remain constant. Right, yeah, let's have a look at something called a diode. You ever heard of a diode? If you've heard of an LED. So the symbol for a diode is quite evil, actually. It's this thing. It's a triangle with a line across its nose and a straight line going not through the triangle, but on either side with a circle around it. That's what a diode is. I'm not going to tell you what a diode does. I'm going to show you. You can get diodes, and you can get diodes that give off light. They're called light-emitting diodes, or LEDs. That's what an LED is. It's a light-emitting diode. So what does a diode do? How many times can I say diode in a sentence? Let's find out. Got battery, wires. I'll just stick a diode in. Yeah. Excellent. So this is working. It's just a little bulb lit up, as you might imagine. Let's measure the voltage across the diode for good measure. And there we go. Brilliant. About 3 volts. Okay, now I'm going to turn the diode around. What are you expecting to happen? Oh, can IGCSE physics get any more exciting? Gasp! Nothing! The bulb is not lit up. What is happening? If I plug in my voltmeter, what are you expecting to see? That's a good question, isn't it? I plug in the voltmeter, what are you expecting to see? What's the voltage across this bulb now? double gasp. It's the same. What? So we've got current flowing through this circuit. We must have. There is a charge. There's energy per charge across this bulb, but it's not lit up. What's the explanation? Well, the explanation is a diode is something that only allows current to flow in one direction. That's all a diode is. A diode only allows current to flow in one direction. A light emitting diode just happens to be a diode that lights up. You can see the symbol for a light emitting diode is the same as the diode, but you've got two little arrows coming off to show light. So yeah, these are incredibly useful for all kinds of things. It's not how it works, but a description of how it works is in one direction, diodes have an incredibly high resistance. So that's why we had a voltage across it, the circuit was still working, but it wasn't lit up. It was just that the resistance is so high in one direction that barely any current flows, so that the bulb wasn't lit up. But in the other direction, it's actually got very, very, very low resistance. It's very easy for current to flow. That's why if you were doing an experiment where you made a circuit that had a diode in it, you would always put a resistor in the circuit. You see that on the bottom here? They've stuck a little resistor to this sort of toy diode, because otherwise you'd be very likely to kind of melt your bulb if too much current went through it. It wouldn't be a fun explosion. It would just sort of start to smell like plastic burning, and you'd get smoke coming off. But yeah, you add a resistor so that gives it a bit more resistance, so slightly less current, so protects the LED. Okay. What does a graph for a diode look like? This is tricksy because suddenly direction, the negative and the positive side, does come into it. I've given you a clue. I've said resistance is very low. What does a graph of current and voltage look like when the resistance is very low? And not expecting you to get this right. Again, if you've printed out the worksheet for this, you've got the answer in front of you. So you can challenge yourself and sketch it with voltage on the top on the y-axis and current on the x-axis. And I will prepare to do the same. Sorry. Squeaky board rubber. I'm just going to give you 5 seconds because I think this is hard, but good practice to not just give you the answer straight away. 5, 4, 3, 2, and this is the last thing we'll do, by the way. And then I'll give you a little quiz, and then it's the end. Okay, it actually looks like this. It's totally flat on one side, because in the negative direction, you can try and push that current through as much as you like, do a really big potential difference, like -8, -10. You're still not going to get any current to flow because the resistance is so big. But on the other side, resistance is low. So for not very much potential difference, you get loads of current. Okay, if you want to do this with me, that would be great. I'm going to try and do it the other way round, just in case they try and trick you like that. So if you go to BBC Bitesize, you'll find all the graphs that we've shown you, like all the ones I've had on the board. That was the diode that you'll get. But it's always worth knowing how to sketch it in different directions. Very good practice. Right. So, a diode. Well, the negative side is easy, right? So this is the voltage. So when it's negative, it's going in the sort of wrong direction. Voltage can be really, really, really big, but there's still no current flowing. So this is the current axis, so that's zero current. So you're always going to get zero current. So I'm going to draw a line like this to show that even when there's loads of push, you don't get any current flowing. That's right, isn't it? And then on the other side, resistance is very low. So a little bit of voltage gives you a lot of current. A little bit more voltage would give you loads more current. A little bit more voltage will give you loads more current. Okay, right, yeah, that's not too bad, that. Yeah, I'm getting quite good at this. I think I'm almost ready to do IGCSE physics. There we go. Oh, I shouldn't tail off at the end. Right. That's the end of that. What a lot covered today. Very well done. Very well done for sticking with this the whole way through. I'm going to give you just 4 sort of multiple choice questions to see how much you've gained today. And then, as usual, in my Facebook group, I will at some point, I'm actually going to the theatre tonight, so probably not tonight, but at some point I'll put in my list of like extra reading that I think you could do, or past paper questions that I found that you should be able to answer now, so that hopefully you can kind of piece all this together in your head in your own time. If you're enjoying these lessons and you want to support me, you totally can. It's the only way that I make money is by lovely people going to this website called Coffee. It's in my About section, on YouTube, which is where you are now. But if you just search Coffee Theatre of Science on the internets, then then yeah, you get this website. You can support me with £5 or £6 a month. Just got a lovely email from someone saying, "Oh my goodness, I just paid for another cheap science lesson, and it's really made me appreciate your work," which is sort of nice. So if you want to support me with £5 or £6 a month, if you think that these lessons are worth that, I'll send you thank yous. I'll send you some rainbow glasses. They make you see rainbows. And I'll send you my 2-page explanation of how they work. And I'll send you Theatre of Science magazine. If you sign up now, I will send you my magazine on mould, which comes with a free biodegradable plastic bag. It's got a cartoon all about the discovery of penicillin. It's very good. And then you'll get the sleep issue, which is coming out pretty soon, next couple of weeks. Okay, thank you very much. Here are your multiple choice questions. Which one is the fixed resistor? You've got 4 circuit symbols here. Look at them carefully, because I might get you to sketch one in a minute. Which one of those is a fixed resistor? Is it the triangle with the line across its nose and a line going through it all in a circle? Is it that, but with arrows coming off it? Is it a rectangle with a line through it, or is it a rectangle with no line through it? 5, 4, 3, 2, 1. It's the rectangle, with just a line on either side. Question 2. Which of these graphs shows the highest resistance? You've got 2 graphs. They've both got current on the y-axis and potential difference on the x-axis. They're both straight lines, but one of them, the first one is quite steep and the second one is quite shallow. Which one shows the highest resistance? 5, 4, 3, 2, 1. This one, you've got a really big push, but still hardly any current flowing. So if you're really trying to push with your potential difference, the current through, and you're not getting much, that must be because the resistance is very high. So it was the second one. Well done. Question 3. What's wrong with this graph? Potential difference is on the y-axis, current's on the x-axis, it's just a straight line. I mean, there's actually quite a few things wrong with this graph. Bearing in mind what we've talked about today. What's wrong with this graph? 5, 4, 3, 2, 1. I was trying to catch you out. I thought you might say that potential difference and current are on the wrong axes. That's not exactly wrong. There's no units, are there? There's no units. You've got to say that potential difference is measured in volts and current is measured in amps. This is really important because it's quite likely that you would do an experiment where you measured the current in milliamps, and if you don't say that, all your maths is going to be wrong. Sketch a light-emitting diode, finally. Sketch a light-emitting diode. I should say, this is badly worded, I should say draw the circuit diagram for a light-emitting diode. I've just realised this. You couldn't just sketch me a beautiful picture of a light and get any marks. What does a light-emitting diode look like, the circuit symbol? 5, 4, think about your lines. 3, 2, 1. It looks like this. A triangle with a line across its nose, and then the line is going sort of through it, but not through the triangle, and then there's a circle around it, and then some arrows. It's quite tricky, that, isn't it? Did you remember the arrows? Probably get 1 mark for a diode. Okay, you lot. This is on YouTube, so I'm just going to go over to my Facebook page and see if anyone's left me any messages. But your brains might have melted too hard to leave me any messages, but we'll see. I always, when I'm on YouTube live, I always put a little post up on Facebook saying, hey, if you want to say hello or ask me any questions, then you can. So let's see. Maybe Chloe said hello. Wait, here I go. I follow Draw with Rob on Facebook. You know Draw with Rob? And he's just posted something about World Book Day, and my heart just went, it's World Book Day! My children aren't dressed up! It's okay, it's not World Book Day yet. Stand down, everyone. Oh, someone else said hello. Who's this? It is Chloe! Hello, Chloe! I hope your brain hasn't melted. Oh no! Jack can't find the lesson. Jack, there's no point in me even responding to that because maybe you're not here. I'll go and see if you found it. All right, you lot. Thank you very much for coming. Chloe, have a lovely rest of the day, and everyone else who's watching, I hope you have a lovely day, and I'll see you next week for another IGCSE lesson, or tomorrow, maybe, for a Lego Storytime show about snails. That will be on YouTube at 2 o'clock. You need to bring some plastic from your recycling, and some paint and a pair of scissors. And we will learn all about snails and how amazing they are. Okay, yep, see you very soon. Thanks for coming.